Let's discover how the formal definition of a derivative emerges from a simple geometric idea. The derivative measures how fast a function changes at a single point, capturing the instantaneous rate of change. We begin with something familiar, the average rate of change between 2 points. Consider 2 points on a curve, one at x and another at x plus h, where h is some distance away. A secant line connects these 2 points, and its slope gives us the average rate of change. The slope of this secant line equals f of x plus h, minus f of x, all divided by h. This fraction represents how much the function changes on average as we move from x to x plus h. Now comes the brilliant insight that leads to the derivative. As we make h smaller, bringing the second point closer to the first, something remarkable happens. As h approaches 0, the secant line approaches the tangent line at the point. We express this mathematically as h approaches 0. We formalize this process using the concept of a limit. The limit as h approaches 0 of the difference quotient gives us the instantaneous rate of change. This limit, if it exists, represents the slope of the tangent line at the point x. We call this f prime of x. This is the formal definition of the derivative. Let's break down each component of this definition. The numerator f of x plus h minus f of x measures the change in the function's output. This represents the vertical change, or rise, in the function. The denominator h measures the change in the input. This represents the horizontal change, or run, along the x-axis. Together, rise over run gives us slope, just like in basic algebra. Let's see this definition in action with a concrete example. Consider the function f of x equals x squared. Applying our definition, f prime of x equals the limit as h approaches 0 of x plus h squared minus x squared, all over h. Expanding x plus h squared, we get x squared plus 2xh plus h squared minus x squared, all over h. The x squared terms cancel, leaving 2xh plus h squared over h. Factoring out h from the numerator gives us h times 2x plus h, all over h. The h's cancel, leaving us with the limit of 2x plus h as h approaches 0. As h approaches 0, we simply get 2x, so the derivative of x squared is 2x. Let's visualize what this derivative tells us geometrically. At any point on the parabola, the tangent line's slope equals 2x, telling us how steep the curve is at that exact location. The derivative at each point gives us the slope of the tangent line at that point. Let's review how we derived the definition of the derivative. We started with the familiar concept of average rate of change between 2 points on a curve. Then we let the distance between these points approach 0, moving from average to instantaneous change. We formalized this process using limits to arrive at the precise definition of the derivative. This gives us the fundamental definition: f prime of x equals the limit as h approaches 0 of the difference quotient. This beautiful formula captures the instantaneous rate of change, the foundation of differential calculus.